our goal is going to be very simple. Suppose we're given a set of throws. Can we be sure that it corresponds to something that can be juggled? In other words, we can think of a siteswap as a set of numbers, and we can say, okay, suppose that we grab some balls and throw according to those numbers. Will we succeed in juggling? Or will something terrible happen? And how will we know? How will we know? Well, we're going to answer that. Okay, so let's think about it. Here's our convention. We'll say that a sequence of throws is jugglable, which is a very fun word to try to say, if there are no collisions. Well, what's a collision? Well, a collision is when we have two throws that are scheduled to land at the same time because the balls will collide. So that's what we want to avoid. All right, so now what we really can say is the question of whether something is juggable or not juggable comes down to, are there collisions or are there no collisions? And so we want to figure this out. So what do we have? Well, we know that we're making certain throws for every single beat of time. So we're going to let t sub I be the throw made on the ith beat. So in other words, when we reach time I, that's how far we're going to throw it. Well, what do we want? Well, if we think about it, let's suppose this is time I, and this is time j. And this throw, in other words, how far are we throwing? See, that's what siteswap is telling us. How far do we throw things? Let's say that this is thrown so it lands ti beats in the future. This is thrown so it lands tj beats in the future. And now we want to make sure that when I add the starting time plus the time it's in the air, that's I plus ti is when it lands. In the same way, j plus tj is when that ball lands. We just want to make sure that they don't land at the same time. So that whenever I look at two balls thrown at different times, they're going to land at different times. Now, of course, they may land in different relationships to one another. That's not the important thing. All we need to make sure is that we never have two balls thrown at different times landing at the same times. If we know that's true, we can juggle it. All right, so how do we figure this out? Now, one thing we don't want to do is say, all right, we've got infinitely many throws, right? Because we've always been juggling, we'll always be juggling. We don't want to test all infinitely many throws. We want to simplify things. So let's think about how we can do that. And this comes back to what we talked about with modular arithmetic. Instead of thinking about the line, we think about the circle. Because now, if we can think of things in that context, it really reduces things down. So we have our throws. So that's our siteswap, T1 through Tn. Well, it's a potential siteswap, right? We should think of siteswap as things which actually can be juggled. So what do we have? Well, we can say that the balls that are thrown at times congruent to I mod n will land at times congruent to I plus t sub I mod n. Now, you might say, wait a second, we just said that, right? I and I plus t sub I. What's new? Well, this equivalence or congruence. By the way, congruence is another way of saying equivalent modulo n. So what we want to do is say, hey, look, at one beat, I know what's happening. But because I'm repeating this pattern every n beats, I'm allowed to say, look, if I know what happens here, I can shift everything by n to the next block. And I can shift everything by n to the next block. And what will happen? Well, because I'm making the same type of throw, all I've done is offset my starting time by some multiple of n, then the ending time will be offset by some multiple of n. In other words, modulo n, everything's great. And in fact, a couple of nice things happen. When I'm looking at the same times congruent to I mod n, they're the same types of throws. So they're all going to have the same length of time up in the air. In other words, they're not going to collide. See, if these are offset by n, they have to be the same throw length. So however much they're offset here is however much they're offset when they land. It's not like I'm going to, wow, go. No. They're the same throws. So no collisions when I throw things at the same time. Okay, that's convincing. And then it actually goes a little bit further. It says, when I look at where they land, because they land in something mod n, and it's going to populate all those entries. Why? Well, because look, wherever it lands, I can shift by n, and that comes from starting 1n earlier. Or I could shift by n the other direction. That was one step later. And therefore, I'm going to saturate that congruence class or that equivalence class modulo n. This is the key observation. So far, it's nothing too surprising because it just says, oh yeah, things are periodic, and so we can translate things periodically. And this nice thing about modulo n, just it collapses things down so that we only need to understand one period. We don't have to understand the infinitely many throws. One block, that's enough. So, how does it work? Well, what we say is, look, this pattern where we have these throws t1 up through tn will be valid if and only if, when we look at the numbers 1 plus t1, the next one would be 2 plus t2, 3 plus t3, all the way up to n plus tn are distinct modulo n. Well, why? It's an if and only if, so that's a strong statement. Well, if they weren't distinct, what would happen is that you'd have two different times when you throw from two different equivalence classes, modulo n, and you land in the same equivalence class. But remember, we said that you saturate, which means there's no spare room. There's not like, oh, we'll take turns and alternate as we go off to infinity. No. You're going to hit. Collisions. Bad. It can't be juggled. Now, if they are distinct, then that says, look, nothing can interfere with anything else, and life is good. So this is now a very quick and easy test. But remember, you have to take things modulo n. It's not just enough to say these numbers are distinct. You have to ask yourself, what happens modulo n? So there's our test. Pretty easy, right? All right, well, that's good. Means we can do some examples. So let's start with this example. Determine which of the following is jugglable. And we have some patterns: 4, 6, 7, 7, 4, 1, 6, 2, 7, 4, 2, 1, 6. All right, 3 patterns. So hopefully something's jugglable. What can we do? Well, let's just pick a pattern. So we'll start with this one. We'll call this one number 1. Now, what do we do? First off, what's the period? Now, when we see this, it's not the number 467. Yes, it's bad notation in that regard. It's a 4, a 6, and a 7. But it's a notation that we've learned to live with. What's the period? Period 3, right? Because there's 3 numbers. So what we do is we say, okay, here are the throws. So 4, 6, 7, those are our throws. Then we have our times, 1, 2, 3. If you don't like the word times, you can think of it as your beats. So at beat 1, we throw 4. At beat 2, 6. At beat 3, 7. And now we're going to add them up. And again, these are separate values. 4 and 1 makes 5. 2 and 6 makes 8. 7 and 3 makes 10. Okay, so we've added up the throws plus the times we threw, or what the beats are, and we got 5, 8, and 10. Are we done? Is it jugglable? Well, we're not done. What's the other thing we have to do? Now, we got to take this modulo our period. So in our case, modulo 3. And when we do that, okay, what do we get? 5 mod 3 is 2. 8 mod 3 is 2. And 10 mod 3 is 1. And now, are these distinct? And the answer, no. See, those are equal. So that says 4, 6, 7, not jugglable. Can't be juggled. Can't be done. You're always going to have balls colliding. All right, and that's it. That's how the test goes. So we'll do it a couple more times. By the time we're done, we're going to be really good, right? Okay, so let's go and try our second one. 7, 4, 1, 6, 2. All right. So here we go. 7, 4, 1, 6, 2. Our throws. Underneath it, we'll write down the beats. 1, 2, 3, 4, 5. Add things up. 7 and 1 makes 8. 4 and 2, 6. 1 and 3, 4. 6 and 4, 10. 2 and 5, 7. Okay, promising, but we're not done yet. What's our next step? Modulo 5, because this is a pattern of length 5. All right, so let's see what happens. Mod 5. What do we get? Well, 8 mod 5. Subtract 5 off. That would be 3. 6 mod 5, 1. 4 mod 5. It's good to go. Don't need to do anything. 10 mod 5. Well, I like 0. We could do 5 as well. 7 mod 5, 2. And what do you notice? They're all distinct equivalence classes. None of these equivalence classes are the same, which means that this one is good. It can be juggled. Now, we're not claiming it's easy to be juggled, but we are claiming it can be juggled. And so, there we go. Something that perhaps we could learn. Maybe. All right. Well, let's try another one. After all, there is another one. We should try it. 7, 4, 2, 1, 6. Now notice, this has the same types of throws. We've just rearranged them. So we have the same. In fact, really, what have we done? We've just moved the 2 over. Okay, how bad could that be? Could it really cause any problems? Let's find out. Okay, so let's see. We'll do it right underneath this one. How's that? All right, so 7, 4, 2, 1, 6. Underneath it, 1, 2, 3, 4, 5. Add up the numbers. 7 and 1, 8. 4 and 2, 6. 2 and 3, 5. 1 and 4, 5. 6 and 5, 11. We don't even need to do anything else. Look at that. There's 2 5s, a 5 and a 5. They're equal. So they're definitely going to be equal mod 5. So this one can't be juggled. Now, if we went ahead and just carried out the computation, which we have paper, we have time, what would happen? Well, we'd end up with a 3, a 1, a 0, a 0, and a 1 again. And in fact, we have more than one potential problem. We actually have 2 potential problems. So this says it's sensitive to the order of the throws. Just because you have some set of throws in some order that does work, rearranging can ruin things. So you have to be very, very careful. It's a delicate line. So it's not like it's going to be easy to make these siteswaps that are juggable. It's not trivial. In fact, the longer it is, the harder it is to make something which works randomly. So let's try something. Let's create a valid siteswap of length 8. 8! Wow! That's a long one. So if we just wrote down 8 numbers, well, we could write down 8 really boring numbers like 0, 0, 0, 0, 0. No. Let's try to make it interesting. Let's just try to sit down and find something. Make something new. Something that's probably never been made before, and who knows if it's ever been juggled before. So how are we going to do it? Well, let's just think about what we have to do. We'll just be careful as we're creating it to make sure no problems come along. All right, so here's the idea. Or at least here's one approach. There's more approaches. We're going to learn how to generate all patterns eventually. So let's think about what we could do. So I'm going to think of it as I have 8 boxes to fill. So I'm going to draw my 8 boxes here. And my 8 boxes are the throws. So let's see, how many is that? 5, 6, 7, 8. All right. And now those are going to be my throws. And underneath it, I'm going to write down the beats. So time 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to keep track mod 8. And just the key is, we just want to make sure that whenever we add in a new throw, it doesn't create a problem. Okay, now I want to convince you that I'm being fair about this and I'm not just picking things predetermined. So, I have come up and found a random number generator, which will help us pick a couple of numbers to start, and we'll go from there. All right, so we'll just go with the last digit here. What do we have? Our first throw, our last digit, well, it landed on 21, so we'll say, okay, it starts with a 1. Okay, that's easy enough. Put a 1, and now 1 plus 1 is 2, 2 mod 8, 2. The first throw never creates a problem. Now let's pick another digit. So, where are we going to end up this time? I don't know. That's the thing about random. You never really know. And, wow, a 2. Okay, these are very short throws, but that's okay. That's okay. That increases the likelihood that we could actually juggle. Now, let's see. If we put a 2 in here, we can do this in our head. 2 and 2 would make 4. That's fine. That doesn't conflict, so there we go. So what we're doing is that as we go along, we just want to make sure we avoid collisions. Let's see if we can do a couple more. All right, so here we go, making a new selection. Where are we going to go? What number are we going to end up with? Wow, a 3. Okay, can we do that? Well, if we put a 3 here, what would we have? 3 plus 3 is 6. 6 mod 8 is still 6. That's okay. So 1, 2, 3. All right. Well, I hope we don't get a 4 because people are going to be very suspicious about my random generation here. Come on, a 2 again. Can I do 2? No. Why? Because look, if I put a 2 here, 2 and 4 would make 6. Well, okay. We'll try it again. Now, eventually we'll stop and say, let's stop picking random numbers. Let's actually be smart. Okay, that says 3. All right, can I pick 3? Well, yeah, look, 3 and 4, 7, mod 8, no problem. So, here we go. Okay, let's try to do one more here, and then we'll fill in the rest. Okay, come on. Give us something that we can work with. Okay, a 4, right? Landed on something that ended with a 4. If I had 4 and 5, it would be 9, which is congruent to 1. Hasn't shown up before, so we can add it to our list. Okay, all right. Now at this stage, we'll stop doing our random number generation and start thinking about, okay, how can we finish this up? So far, no collisions, life is good. But what needs to happen? Well, if you look, there's 2, 4, 6, 7, 1. What's missing on this list? Things that are missing. Well, so far, we haven't seen a 0 mod 8, a 3 mod 8, or a 5 mod 8. So what needs to happen is that 0, 3, and 5 have to show up in here. So now we can just pick a number. Okay, suppose I wanted to put the 3 here. Now we're going to reverse engineer. I need something plus 6 to be the same as 3 mod 8. Well, what can I do? Well, negative 3 plus 6 is 3, but I can't make negative throws. Well, okay, what's the next thing you can do? If negative 3 works, add 8, because mod 8 says you can add any multiple of 8, and that would get us to 5. Okay, would that work? 5 plus 6 is 11. Mod 8 would give us 3. So 5 works great. So there's a throw. Okay, let's say we could put a 0 here, right? Because we've already put the 3. All right, 7 plus what gets us to 0 mod 8? Well, if we add one more, right? 1 plus 7 would be 8, and mod 8, that's 0. Great. Okay, that leaves us with the 5, and well, what do we need? We need 8 plus something to be congruent to 5 mod 8. Well, of course, adding 8, it's really, since we're doing mod 8, it's the same as adding 0. So I can make this a 5 as well. So 1, 2, 3, 3, 4, 5, 1, 5. That is a valid pattern. That can be juggled. And it's not impossible. Indeed, this is probably something that with patience could be learned. It probably isn't the most beautiful pattern, but then again, most patterns aren't the most beautiful patterns. But there we go. There's a valid site swap of length 8. In fact, every valid site swap could be formed in this way. I don't think it's the easiest way to form valid site swaps, and we're going to learn better ways and more systematic ways to do it. But of course, that's for discussion for another day. All right, good. The last thing for now. Suppose we have something which is a valid pattern. So in other words, this list of numbers, this is a site swap. It can be juggled. We want to show that it must be the case that the average of these throws is a whole number. Okay, wow. So how are we going to do it? Well, let's think about what's going on here and what we can learn. So we know we have a valid pattern that can be juggled. Okay, and we want to show that the average of these numbers is a whole number. So what's the average? Well, it's T1 plus T2 plus so forth and so on up to Tn, and then you divide by how many numbers there are. In this case, divide by n. That's the average. And what we want to say is equal to some whole number. Okay, so we can say that's a natural number because all these numbers are greater than or equal to 0. So when you see in n here, this is a bold n. That's a shorthand for saying it's a whole number, a whole positive number. Okay, so where to begin? Now, one way we can think about it is to say that means that n divides this. So really, this is the same thing as saying that we want to show the following, namely that T1 plus T2 plus so forth and so on up to T sub n is congruent to 0 mod n. These are equivalent statements. To say that n divides a number is the same as saying that that number is congruent to 0 mod n. All right, well, that's something, right? So where will we begin? And how does this relate to what we've done today? Well, what have we talked about today? We've certainly talked about stuff mod n. Okay, that's good news. And the punchline is that if we have something which is valid, that when we look at the throws plus the beats they came from, and we looked at things mod n, they're distinct. So let's just put that together. And so, what can we say? We can say the following. If we start with these values, so T1 plus T2 plus so forth and so on up to plus Tn, is certainly equal to 1 plus T1 plus 2 plus T2 plus plus n plus Tn. Now, I'm not done yet, but okay. These we should recognize, oh yeah, these are the landing times. But we can't say it's equal yet because we've added these numbers in. So that's okay, we'll just subtract. So 1 plus 2 plus up to n. All right. So now I think we can agree, yes, you've added 1 plus 2 up to n. You've subtracted 1 and 2 up to n. So you're back to where you started. Okay, so here's the cool thing. When we look here, and we look at things mod n, what will we see? Well, we're going to see somewhere there has to be the number 1, somewhere there has to be a 2, somewhere there has to be a 3, and so forth and so on, all the way to somewhere there has to be an n. They're distinct, mod n. And see, mod n, when I say I have n things to put in these n slots, and they're all distinct, that means every slot gets filled. Everybody's there. They're all represented. Nothing's missed. Nothing's missed. So this is going to be congruent to the numbers 1 plus 2 up to plus n. That's from these parts, modulo n, rearranged in some way. Then subtract off these parts that we've added here, 1 plus 2 up to n. And this is done mod n. So the first step is an equal. The second step is an equivalence, where we're using modular arithmetic. But now we say, aha, if I add a bunch of things and then I subtract those same bunch of things, that's 0. And now we're done. We're done. We showed what we wanted to show. So this is great. Well, why? Now we have a very, very simple test. So for example, is 4, 4, 3 a pattern? Or we can even say a siteswap. And now we don't even have to do the whole test, right? We say, well, what's the average? 4 plus 4 plus 3 is 11. 3 doesn't divide into 11. The answer is no, because the average is not a whole number. All right, now be careful. We're claiming here that the average is a whole number. That doesn't mean that when the average is a whole number, something is juggable, right? Because there's two statements. I can be juggled, the average is a whole number. So if you can be juggled, it is the case that the average is a whole number. It doesn't have to work the other direction. So for example, is 5, 1, 3 a siteswap? Well, if you take this and add up the numbers, 5 plus 1 plus 3, you get 9, and 3 divides 9. But you can check, you can even just do it really quick here. If I have 5, 1, 3, let's see, what'll happen? Well, 5, 1, 3, 5, 1, 3. This'll cause what? See, this 3 will land 3 beats in the future, and this 1 lands 1 beat in the future. Collision. So be careful. Remember, there's a difference between if and only if. So make sure you're paying attention. And one quick preview. It's a whole number. What is that number?